A while back we looked at Bolzano's theorem, and you might be wondering where this theorem is relevant. So the bisection method, which we're going to discuss right now, is exactly the place where Bolzano's theorem applies, because what we're trying to do, once again, is we're attempting to solve the equation f of x equals 0, and let's actually do a plot so that we can see what it's all about. So here is a plot of the y and x axes, and let's suppose that there is some function that goes kind of like this, and we want to find out the intersection, as always. Now, what the bisection method basically says is that we can make an educated guess about the range in which the solution is. So, for example, we can do a plot and we can say, well, if there is a point A here and there is a point B here, such that f of a actually gives us a negative value, as can be seen here. So this is going to be f of a, this location. And similarly for f of b, we get a positive value somewhere here. So that would be f of b. What we can say is that we know that the solution is between a and b if the sign changes. And that's what Bolzano's theorem was all about. So essentially what we can say that if f of a times f of b is negative, then we know that the solution is somewhere between a and b. So then the bisection method basically says, well, you've got this range, how about dividing the range in half? So we find a middle point, let's call it point C. And then we consider the sign change between A and C and the sign change between C and B. And there are two possibilities here. So one of the possibilities is that when we calculate f of A, f of C, this is less than 0. So that's one possibility. The other possibility is that we get f of C, f of B being equal to 0. Or less than 0 rather. So if f of a and f of c, if their product is less than 0, that means that the solution is between a and c. If the product is less than 0, f of c, f of b, then we know that the solution is somewhere between c and b, once again leveraging Bolzano's theorem. So in this case, we have f of a times f of c less than 0, because if you look at the picture here, you'll see that this is where the solution lies. So once again, we get a value of f of c. F of c is positive, f of a here is negative, so we know that their product is going to be negative. So we know the solution is between a and c, and once again we do a bisection. So once again we subdivide this range from a to c in half, and we once again, let's call this point D, we once again perform the same consideration. So we look at f of A, f of D, and we look at f of D, f of C. And we say, well, which one of these is negative? So this time round, we can see that f of D, f of C is negative. Because once again, if you look at the actual plot, you'll see that f of D gets negative here, f of D, and f of c is positive, so we choose this particular option, and we continue this onwards and then onwards until we get a suitable result. So this is the whole point of the bisection method. Alright, let's take a look at an example of the bisection method in MATLAB. So first of all, what I'm going to do is I'm going to take the function that I want to solve for, I'll define it here, and I'll do a function plot of this function on a range from -5 to 5. Alright, so here is the actual plot. Let's do a grid so that we can see what's going on. Here we go. Okay, so you can see that if we look at the zeros here, you can see that the 0 is somewhere between, let's say, 2 and 3, more or less. So that's our guesses. So A is 2 and B is 3, and that's what we begin with in terms of trying to find the solution. And we specify the number of iterations that we're prepared to do in order to actually find the roots, and we specify some sort of tolerance. Now what we do then is we take a look at f of a and f of b, if their product is greater than 0, then we say that there is a bit of a problem because the function has the same sign. So it doesn't actually, the solution isn't actually between a and b. However, if the product is not greater than 0, then we can actually perform the iterations. And for each of the iterations, we find a midpoint. So here it is, a plus b divided by 2. And we also calculate the actual value of the function at this point. So here is fp. And then there are a couple of options. So one is that we've already found the solution, which would be excellent. But it's also possible that the actual value that we find is either indicating that the solution is to the left or to the right. And depending on this, we actually perform the appropriate assignments. So as you can see, if f of a times fp is less than 0, then we choose b to be the right point. So essentially we're using a and b as left and right. So we're saying the right point is now p, otherwise the left point is now p. And we repeat the whole iteration once again. So as I run this, you'll see that we've done 10 iterations and we've gone through a couple of values of a, b, and p being the midpoint, and eventually we get to a result where f of p is sufficiently small. So it's 189th millionth the final result. And if we're happy with this result, this is where we actually stop the iteration, or we could continue forever.